Let's maybe directly start now with the panel, and then we can also discuss any individual questions that would have come for your presentation, Gianluca. So what I would like to do is a little bit also reflect what we learned in the conference and then put it into a bigger context, but have then still the focus on IBC. But and actually, I really just, again, even if you're not sitting on one table or in one room, just have it casual and that we just talk to each other and everyone can say something. I try to also integrate as much as I can the audience so that we really have a big room talking to each other. Maybe let me just throw in the first keyword or question. So when you've been all in solar for such a long time, and IBC is there from the beginning, right? So when you've been in touch with IBC first, and when you see where it is now, are you actually surprised or disappointed? Is this what we would have expected, or where it would be today? Maybe give it first to Doug, because he has his hands-on experience every day.
I'm thrilled with where we are as a company and as an industry. It's certainly having a lot more impact than people outside the industry had predicted. I think back to our first generation with the instruction that we were trying to make a 20% cell, and then our CEO said, well, it's got to be 20% minimum. And that was a really big deal. It made, oh, how are we going to do this? And then I think through the different generations, the simplifications while still increasing efficiency and the potential for the scale and performance that I think IBC can get to. It's exciting, and I'm glad to see it.
Okay. Whoever wants to say something, just raise hands and then start.
Maybe about the low-cost IBC. So I would, let's say, 5 years back, I would not think that we will come with Zebra above 23% in production, but I also was not thinking that PERC will come above 22% that easily. But because Zebra is based on PERC, you know, like everything is improving incrementally, like better pace, better passivations, and mostly important, the material. So you can see it when you look at Gianlucca, there are no impurities in silicon, so he has to move to perovskites, where there are a lot of impurities. And so I think that like Longi and all the crystalline silicon producers did a very good job to put, let's say, material out there which are performing almost as good as float zone. So it's quite easy now for us to make high efficiency solar cells on them, even if it's with standard processes.
What do you think, Charlie? You've been also...
Well, yeah, a couple of thoughts. I'm first reminded of the expression that we tend to overestimate what we can do in the short term and underestimate what we can do in the long term. And much of the progress, as Doug was talking about, the hurdle to get to 20%, I was thinking about our friend TJ Rogers threatening to take a hammer to anything that wasn't 20. And we were scrambling to find the few things that were. And that was about 15 years ago. It wasn't all that long ago where it seemed like that was the 4-minute mile barrier that had to be broken. And the continuous improvement that we've seen, and there's a reinforcement that comes from having markets for what we manufacture, that has enabled the rapid cost reduction to continue over time. I'm always surprised that effectively we're following Wright's law that is related to the cumulative doubling track of how much the cost can come down and how predictably it can come down for scaling. In solar, we've had the market evolve from satellites to mountaintop repeaters to diesel genset competition to edge of grid and now mainstream grid. And each of those inflections of the market elasticity enabled the scale of manufacturing to continue to grow. And that scale driver has proven itself not just in our industry, but in so many industries that are amenable to the continuous improvement opportunity we have with a manufactured technology. And what really excites me a lot is to think about the rate at which storage costs can plummet, because the market for storage, not just for electric vehicles, but for grid stable storage with wind and solar integrated. The alluded to the target of 1,000 gigawatts by 2030 with PV. Elon Musk's target of 20 terawatt hours per year in 2030 at 10 terawatt hours for stationary storage and 10 terawatt hours for motive transportation for mobility. Those are easy numbers to remember. I just have to remember how many zeros go with which of the technologies. But the market of the speed with which storage costs can plummet, because the market is there in the EV world and the market is there in the evolution of microgrids to improve our grid systems globally, the storage, the PV, and then effectively autonomy, the digitization of things. So the autonomous grid is the mainstay of the evolution of the microgrid world here, bringing solar with storage, with wind, and autonomous electric vehicles. So increasingly, we don't all need to own cars to get around Los Angeles or Washington, DC, or New York or Paris. The ability to have autonomous transportation helps reduce the total footprint of vehicles, and to have them be electric vehicles and still scale helps vehicles become affordable. So with affordable EVs, affordable storage, affordable PV, you can actually make a gargantuan dent in getting to that 80% of our greenhouse gas reduction over the next 10 years. And just as it seemed audacious 15 years ago to be able to mass produce a 20% cell, I think an audacious goal is actually within our reach here. And we need to have government policy align with that. But I'm thinking that the reason the opportunity is here is that manufacturing can scale locally and get to a critical mass. And it's Gandhi-like self-reliance, breaking free, being held hostage to fabric from mills in the UK that were using hydropower by, I don't know if we have to spin our own thread and weave our own fabric, but we can manufacture what we use locally and collectively. Because we're manufacturing clean energy, we collectively enable that attack on greenhouse gases. So there's an interplay here that I think is a wonderful context, that we see the little pieces day in and day out, but in aggregate, it's why I get up out of bed every morning. There's a lot more we can get done, and we can get it done still within my lifetime, God willing here.
No, yeah, yeah, Gianluca, maybe you on that, and then we can.
The question was experience in manufacturing IBC cell. I maybe transfer it into what we need for Tandem. And you can imagine that here you are combining two different type of solar cells. So silicon, we know everything. Perovskite, or let's say thin film, need completely different type of expertise of capabilities from the engineer, the tool that are being used. However, if I make a relationship with heterojunction, it was similar. We had people that had a lot of experience in the amorphous silicon type of thin film that actually joined the more bulk crystalline silicon cell community, and then develop and bring it up the so-called aluminum BSF with the with the passivating contact of the amorphous silicon to the next level. So if we look at that, we can say the industry have already done it. Probably somebody that have experience in heterojunction have the fundamental for understanding the difference, but you can imagine that those are two different fields. You need really two different industrial capabilities there. For 2T, you need them in the same factory. For 3T, pretty similar. For 4T, you can have it even different part of the world, because one side can manufacture the crystalline silicon with the most effective value chain, and the other can be manufactured anywhere else. And the integration in a third country, maybe where you are going to utilize them.
Okay, and I think, but maybe that's a good point, because I think Charlie brought in the bigger picture. I was first talking mostly deep about technology, but I think he's of course right. There's more to solar than this. That's probably what all of us is driving, and I think there's an interesting point actually with the coming of high efficiency technologies, that there is of course also a chance that we're seeing that that manufacturing also will take place actually closer to where it's used, and I've been always the last one asking for protective measures. I've been actually always fighting it very hard, but I think from a sustainability point of view, obviously that makes sense, and so the question is actually really, and I think Charlie is trying to show that also now in the US with Violet, how much is there actually a chance for all this new research that's available here now, and with all these different approaches, to establish something that enables actually countries, regions to become somewhat more self-sustainable. And I just look at reality in a world how it is today. It makes probably also somewhat sense, not that we're kind of getting protective or so, but at least when we see that solar at some point for sure will be the dominant source of electricity generation worldwide, that you don't rely just on one single country that sits on everything. You didn't want to have that in the past, and probably you don't want to have that in the future. So long intro, but so if we look at all these technologies that we've been discussing, and that also maybe with IBC, how much does that give us a chance, or countries or regions a chance actually to get into manufacturing again?
Maybe I can start here with some consideration, and it starts with the graph that Radovan showed at the beginning of what the work that we do, what we have been doing in the past 10 or 20 years with this rapid decrease in the cost of manufacturing. I think what we did was to demonstrate that nearly from no experience you can start start to produce solar cells and module. The industry is mature. There is an excellent tool supplier. You can buy of course, a turnkey line. But there is one new part that I think was key in the past probably 5-7 years, is the value chain. So you can transport actually the equipment to produce wherever it's needed to install, but you need also to construct the ecosystem surrounding that. So you cannot rely on making only the solar cells and maybe making some modules. You need to rely nearly in the full value chain. Also because what Charlie was saying at the end, the energy content, especially on the silicon part, is very high. So you want to produce your panel with the cleanest energy as well. So it's not only the cell, it has to be everything. The problem became not only the manufacturing, but also the value chain, the material need to be there. But one of the things we have heard also from the ITRPV is because of this cost of the module is so low, now the transportation became a pretty large component. So you have a leverage, you have a new leverage in there.
Yes, can I maybe continue on the situation in Europe that you also know quite well, Michael, that I think there are a couple of companies that are more or less saying that in Europe we lost the fight in crystalline silicon. Now we have to go for 6N, for 6G, like Tandem. Then there are other companies saying we must go for 5G, but I still believe, as Gianluca said, it's also now time for 4G, like for standard crystalline silicon production, even PERC. And that's also because of the transportation costs. And I'm also complete. I don't agree with, let's say, again, to rise import taxes in Europe, because then the installers would be very unhappy. And but there are other measures which can be taken. And now the modules became so low cost that it really makes sense also to produce locally in Germany as well. And there are now many activities going on. So not only, let's say, Meyer Burger, but many other serious players are now coming. But still, you need a little bit more innovation. So for example, let's say Zebra technology is quite interesting for that. Or we are also working on flexible factories, like we call it FlexFab, that it's possible in one factory to produce different kind of products like PERC and Zebra, because I mean, it's like Lego stones, you know, you can play around with the machines and produce at one time module for utility scale. And if, for example, the rooftop market is getting bigger, then you can react on that. And a couple of years back, people would say that's nonsense because machines are so expensive. So there is no way that a machine is standing there not producing anything. But times are changing. Machines are not that costly. So it's also, let's say, new ideas are coming now onto the market. Something like FlexFab, for example, is something that we could have in Europe that Chinese, I think, at the moment are not interested in.
I think so. Yeah, I think Doug, and let me just introduce, maybe you want to say something else, but I think actually that SunPower is actually a great example, because I think maybe they are also an example for something newcomers are now facing, because of course, with IBC and now coming to the technology and also looking back, it had to face usually with higher costs than the others have, production costs. But nevertheless, the technology was able to get customers and find its market. And so I think maybe that could be also an example to others. You have to, of course, find your value proposition to be able to do that. But maybe Doug, so.
I think that's well said. I'll expand to the bigger question of the in-country manufacturer and globalization. I think the situation right now is very good, and I think it could be improved. SunPower was actually a pioneer in the Czechoslovakia growth for ourselves. We never used float zone. We actually had our director of silicon. We helped set up a JV in Korea to commercialize that. And then some of that technology through cooperation went to China. And if it wasn't for the scaling and cost reduction of TZS and LongG, our costs would be higher. Same is true for the diamond wire, what we did there, and then later working with TZS on it. For materials, the cost of the materials is much lower than if there wasn't the China scale, China pressure on costs, and some of the additional manufacturing outside of China. Where I think it can be improved is what can you do to have more in-country manufacturing without reducing the amount of solar that goes in the world? And that's where I think intelligent subsidies make the difference. Having manufacturing in a country has advantages for that country, and doing something that internalizes those advantages allows that manufacturing without reducing the number of people that have jobs installing and without reducing the impact that solar can make in the world. And so I hope that countries do look for how to encourage the manufacturing, including some supply chain, without disrupting the growth that needs to happen in the industry.
Yeah, I think so. I think what we're discussing in Europe now, and I think the example everyone is looking at is an example of France, where when you participate in the tender, there's also a carbon component actually. So that means you, of course, part of that is price, and then it's an adder actually from your CO2 footprint. And I think if you keep it simple, I think that's a way to go, for example. So and I think it's also good because of course you also see now that bigger Chinese players now are going RE100 or so to become 100% green in the long term. But even if this is the fact, that's also fine. So in any case, but what we're seeing in Europe, at least at the moment, with all these new technologies, as Rado said, really a lot of interest on the one hand, actually from the industry and players to come up with manufacturing solutions. But we're also seeing now politicians waking up and understanding what China understood much earlier than anyone else, that solar is really a strategic asset and not just an alternative energy. So the question is actually also the one on of course the supply chain. So where to get things and where to go. I think what I also found interesting, so I think you mentioned, of course, that you're silver free, Doug, and yesterday we had that discussion between Holger and Leo going on about copper solutions actually in China. But in China, there are these hard environmental guidelines that you cannot do that. And okay, you're produced in the Philippines, but I think for such reasons, it also makes sense to be flexible and not focused on one country. And probably that's also one reason why we will always see some diversity.
Just a quick comment on that, that copper plating. We designed that factory to California emissions standards. And so we feel very comfortable with our impact on the environment there. The question is, in China, will they build the factories to those standards, and will as was discussed yesterday, whether local government officials will look at that data, or whether they will have a blanket ban because of problems and abuses with processes that were not as clean.
Okay. So, Charlie, you also showed very innovative things you wanna do with Violet. So how is the feedback you're getting also from potential customers, and maybe also from the financing world, that you're actually trying to really look beyond what we have today?
We've had fabulous feedback. I've already found customers for the first gigawatt of our production. So that helps enormously with the financing thread here, knowing that there's an outlet for what we make. It's been interesting. Among the venture groups, Breakthrough Energy Ventures is one that has perhaps the highest hurdle related to greenhouse gas reduction for making investment decisions in the venture capital side of things. From the government policy side of things, there's an interesting observation I'll share here, which is in the US, we have a critical materials list. In Europe, there's a critical materials list. The attention to cobalt and somewhat to lithium and nickel from the battery sector has drawn attention, along with some of the rare earth elements that are used in advanced magnets. So the government policy piece that I found intriguing has been policy related to critical materials and securing critical materials that also helps from the standpoint of leveraging finance instruments that are managed here in the US by the government. On the European list of critical materials is high purity silicon. There's 650,000 tons of 11/9 pure silicon produced every year. This is mind-boggling how much pure silicon there is. 80 to 85% is made in China. About 50 to 60% of that is made in Xinjiang province because it's right next to where the coal power plant is. So there's actually a very large carbon footprint for the scale of silicon. And as a critical material, silicon is not on the US list. The US has 35 critical materials, but silicon isn't there. And when you think about how dependent we become on silicon for not just solar, but for microelectronics, the other version of 5G in the telecom sector, is it going to come from Huawei, or is it going to be built somewhere here? Is TSMC going to scale their plant in Phoenix? The supply of that, the root of the critical materials in the value chain, high purity silicon, is where there's been a lot of attention placed on self-reliance. The irony for me, looking 2 days ago, the Secretary of Energy here in the US, Dan Brouillette, opened up the loan program office to fund mining. This it occurred to me, if only the loan program office thought about silicon and the importance of silicon as a critical material, while lending money to dig more holes in the ground, often without the usual kinds of environmental attention that's important. So financing from the government side, understanding the interrelationships, and perhaps more importantly, the continuity over time. Our technology half-life, I found it ironic when trade cases were being discussed here in the US, that one of the plaintiffs in the trade case asserted that they had invented PERC cells. And having thought back to Martin Green and Andrew Blakers and the UNSW team in 1983 that invented the PERC cell, which had already long elapsed in terms of technology. Our technologies have a long half-life. It takes time. Long-term continuity is critical for the government, and the government to have policy related to job creation and critical materials attention. There's some large opportunities across the world related to the government policy opening financing instruments. The scale of manufacturing is not aligned well with the traditional tranches that venture capital invests in, going through Series A, B, C, D, releasing funds slowly. It's part of the reason why what's called a special purpose acquisition company has become fashionable here, at least here in the US, a SPAC, effectively a reverse merger that I first saw in China, actually, when Samuel and his team accomplished reverse mergers that spun it from Solar Tech to JA Solar, to two other reverse mergers, financing instruments and creativity there. A SPAC is pretty exciting because the amount of capital that's raised typically is in the ballpark of $150, $200 million. It allows scale to happen quickly. We can get to scale quickly. We know there's a market, a domestic market that can match scale, and getting to scale gets within throwing distance of anybody's factory anywhere. And the cost to move, if I've been looking at the cost of glass. If I wanted a piece of glass from Malaysia or Vietnam or China, it sits on a boat. That cost is 10 cents for that piece of glass. Once it hits the port, clears customs, gets a truck somewhere, it's actually another 50 cents for that piece of glass to move. So being able to look at our technologies as construction materials, as a materials business, our cost structures are all dominated by yield because we're a materials business. There's an opportunity that drives towards the modularity cost effectiveness that can be done, which being able to explain the opportunity to investors is, I think, key to being able to unleash the financing.
Okay, so when we talk about, I think so 1 point for local manufacturing is sustainability. Let's talk maybe about the product also a little bit, and about how it can made or designed to last for the 50 years Charlie was mentioning. So first of all, of course, we can discuss if it has to, but if we want to. So what are, I think so, for example, there are also questions regarding when we talk about IBC, because you're all looking into that. What about LETID or any PID sensitivity to the technology and your experience? You have seen that, and let's stay a little bit on the talk a little bit about the point of reliability and how we can really make products last very long. And
okay, Michael, so on the degradation level, I already answered in the chat, but I can repeat. So PID is quite difficult to control on N-type cell level, but it can be completely eliminated at module level using good encapsulants. So that's why also N-type is using polyolefins. So no PID when good module bill of materials is being used. Then LETID, of course, it's a combination of LID and hydrogen-induced degradation and depassivation. So LID you do not have in N-type because you don't have boron-oxygen complexes. hydrogen-induced degradation, you can have it if you have too much hydrogen in your system, but this can be, as in p-type, controlled with the process itself. So you should not release too much hydrogen from your additional passivation dielectric into the system. And we are firing our Zebra cells at rather low temperatures, so we have no hydrogen-induced degradation. And depassivation can happen when you are passivating surfaces without any diffusions. Like PERC can have that because they have like a passivating of bare p-type, but of course the IBC technology, and I think SunPower was looking at it also in the past, if no front surface field is present, then also depassivation can happen on the front. But if you have diffusions, there is no depassivation. So at least what we observed from our Zebra modules, they are PID free because of polyolefins, and also LETID free because of all these adaptations.
Okay. And what about when we talk about warranties? Doug mentioned that the product warranty for SunPower is 25 years. We're seeing now that several glass companies, module makers, are offering 30-year performance warranties. I think the first glass, or at least I'm aware of 2 glass backsheet manufacturer using the DuPont Tedlar transparent backsheet are offering actually 30 years for glass backsheet modules. So what are we seeing there, Charlie? What are you looking at when you look at 50-year product? What kind of warranty do you want to offer for your product, or do you think is needed actually? Maybe both.
Well, it's important to maximize the durability. Getting paid for durability is a challenge. The gradually power plant financing has become increasingly confident, perhaps overly so, in the predictability of energy delivery without tightly correlating to quality control. So the quality control in the materials, our polyolefin supplier has extremely tight quality control and consistency. One of the advantages of a polyolefin is it is controllable. Trying to control an EVA extrusion loaded with peroxide catalyst, as well as the stabilizers, UV antioxidant stabilizers, you're pouring it into a giant funnel that's hotter than the lamination temperature. Those solvent systems, especially the cross-linking catalysts, are boiling off during the time they're squished through the funnel and the extruder to make a film. So consistent control of the encapsulant and the confidence that we've accumulated from years of field deployment go hand in glove for the warranty. End of the day, any company needs to be able to either use their balance sheet or have an insurance policy for warranty. So there's a cost that gets paid sooner or later in the reality of what the warranty execution can mean. Our focus on lowering the module operating temperature in the field is partly to not just produce more kilowatt hours, but partly to reduce the thermally driven degradation mechanisms. Doug mentioned hotspots being one example of a thermal degradation mechanism that's localized and sort of aggravates the differences. But being attentive to heat and heat control overall is a good way to look at how to further improve long-term durability. So we make something to last and further minimize recycling questions because it lasts.
So Doug, do you think actually you're selling a premium product, your return rates are, I don't know, negligibly small, but do you think actually the market wants longer warranties? Are EPCs, especially also for bigger projects, looking at that? Is it necessarily, even if we have products that can last for 50 years, to have 40 years warranties, performance warranties, or product warranties that are longer even than what you are offering? So what's your take on that?
I think you framed the question correctly. There's the separate question of how long the modules last and what the warranty is. And when the warranty is based on data that shows the modules will last, that's when customers should really value it. You can buy cheap non-PV products. You just order something on Amazon and it can have a good warranty, and it can be meaningless. Fortunately, the performance of standard products has been very good lately. That there is I think a correct belief that most modules will last well. Not true across the board. There have been some attempts at dual glass modules or different back sheets that have failed. You watch any DuPont presentation and they will detail some of those failures. Some of those companies would close and then reopen under a different name. So having a good warranty because you have a good product, I think, is the key for value for customers and the planet. And to the extent that it is designed to last at least 30, 35, 40 years, you get that, not only that value for the customer, but to not have to be replacing those modules as we continue to scale to eliminate carbon, has value.
Let's talk about also maybe about I think IBC coming out of its niche actually, and that others are maybe getting into that. So I think what I found interesting is it took HJT a few years after the Sanyo patents expired for others to get into that technology and then actually also build on that. So we're seeing at the moment, so this is maybe one thing. The other thing is at the moment we're seeing an interesting situation that there's one company which is at the moment suing a lot of other companies and is also winning cases actually that can cost money. As we all know, in the field of PERC at the moment. So the question is actually, and so if we look at the new technologies, so heterojunction looks sort of patent-free mostly, but if we look at TOPCon, IBC, so how, and I think Radovan, you probably can also look at that because you worked a lot on IBC. So how is the field there, and is this somewhat hindering others from picking up and growing, or so where do we stand, and what can happen?
What should I say, Michael? Okay, let's put it this way. Zebra as it is now, it's not infringing any patents, because we are at the moment we looked at let's say the patents from SunPower, of course, and from other back contact technologies, and at the moment we are safe, because not using any passivating contacts, when you are entering then this area of passivating contacts, this is becoming dangerous. And but as far as we see it, it's there are ways how to make I call it always polyzebras to come to 24-25% without infringing SunPower's or LG. LG has also many patents out there. And but coming to your easier question, which is when IBC will be for, let's say, coming out of the niche market. First of all, I would say that the rooftop market, and this was also stressed by Christoph yesterday, it's not a niche market anymore. It's becoming a big market and huge gigawatts, not only in Switzerland. And let's say for good products for the roof, you don't need only a Switch watch. You can also go for Zebra, which is a more low-cost German watch, maybe. And but every technology that is new will go over the roofs to utility scale. I believe that if let's say you have a big rooftop market and you can improve your technology further, I think there will be some point when you can go to utility scale, and this will be the same for heterojunctions. I don't think that heterojunctions will be for Tandem, sorry, also for heterojunctions, but for Tandem they will be applied on roof first, and then if proven stable, bankability is a big issue there, then they can go to utility scale as well. And let's say Jollywood is also a good example. They have let's say quite low cost TopCon technology, and to my understanding, we have done some cost of ownership and LCOE calculations. There are already situations in utility scale where it makes sense to use NPERT instead of PERC. When you have, let's say, hot regions and quite a lot of reflection from the ground, high albedo, then already TopCon can have lower LCOE than PERC. And this is now happening. And but still, I think the bigger market for TopCon and of course heterojunction is the rooftop market. And
okay, yeah. Doc,
just a quick comment on imagining a world without patent protection. SunPower wouldn't have been able to spend hundreds of millions of dollars on R&D if that was the case. I think that there are some other companies that have been spending money on for their own technologies, Meyerberger with smart wire and heterojunction, maybe even some of the Chinese companies on the new technologies where they're investing in R&D and won't want somebody that has done nothing to be able to just copy what they've done. So at times it can seem like patents are retarding the advances in scale, but the R&D wouldn't have occurred otherwise. And hopefully where there's an opportunity to cooperate or trade patents or do something where it's creating value for the companies involved in the world, that occurs. As far as the niche market, SunPower has stayed at relatively small scale, in large part because of our CapEx was so expensive. It was very difficult to expand. With Max 7, we believe that is now will be a platform that we can scale to a much larger extent. And there you get into the multi-gigawatts of what we might consider niches. I think the citation of Christoph Bailoff saying, a gigawatt a year in Switzerland rooftops alone. You can get to scale that is having a material impact on the world and a very good financial success for the companies involved.
Okay. Gianluca?
Yeah, well, first of all, about niche, I think in this sector, we use it more as a negative term, while it's a more of a obvious step when you enter with a new product. You need to make your back. You need to understand how the product works. You need to understand what your customer wants. It's negative when it remains a niche for too long. and it's negative when yeah, indeed, there is no opportunity, there is no next market to enter. That's the first thing. Then we discuss about IP, and probably in IBC could be easier. We have seen with PERC the difficulties, but I agree that IP are also an important part, because otherwise you don't invest in the research that is beyond the the less competitive one, the non-competitive one that you do in the research project with you, or in general with the government and so forth. You need that investment after all. So IP help to protect those investments. And maybe the third consideration is about why we cannot go beyond the niche market, and for SunPower was not limited by the market, was more limited by the access to the capex to do that. But we need to remind, maybe from the technology point of view, is that you know how long it took to get the PERC on the market, right? Now the IBC is that, plus you need to change the module technology. So you get two change that need to be tested, need to be accepted, and so forth. And we know that the module technology has never changed in the past 20 years. And now in the past 4 or 5 years, it has changed in a way that we got the half cell, we got the shingle, and so forth. Now thinking about back contact is an extra complication. You know, also, you asked me this question other time, why NWT could remain a niche? Well, it's still few gigawatt, but one of the main things was that it was simple on a cell level, but then you need a change on a module level that not everyone can immediately take over, especially because what we discussed about before about capabilities. So far you have a glass, you have a simple interconnection, and then you are changing that. You need to change the system of engineer that work in that. And I'm not saying that back contact is complicated, because actually can be much more automated than the string, but it's a change. And we know every change, especially when we talk about 50 years of reliability, is something that make your hair rise.
Okay. Let me tell you something. Our product now, Zebra, is stringed. So it's a, it's a simple stringed, low temperature stringing product. But I agree with you when going to let's say more advanced processes, like conductive backsheet or the aluminum technology, which will be a complete game changer when it works. But exactly at the moment, it's a simple string module, and that's why it's out there, I would say.
Okay, so I think let's maybe come to final statements. So when we look a little bit, I think as you said, Gianluca, it was incredible what happened in the last 3 years. For many years, not a lot has changed, also not in sizes, in terms of cell sizes, wafer sizes. And I think in the last 2 or 3 years, it was boof on every front. So we had recently an interview with the DuPont guys. Okay, they always point on quality, that's their job. But then actually we heard that the question, isn't it actually not too much what's happening at the moment in solar? Can the industry actually stem that with all these changes, these design changes happening? Or will we see actually, will this bring us a new reliability issue with all these challenges coming at the same time? Or can we handle that while at the same time having to grow pretty quickly?
Well, it's a very difficult question. I think that's why it's quiet. And it's true. I mean, we are changing the module technology. On the wafer side, I mentioned it's a jungle out there. This has an impact, definitely, because the capex is something, it's reduced, but it's still there. If you need to change it every 2 years because we change the wafer by 1 millimeter, it's impossible. How can you keep this learning curve? Actually, the learning curve keep going down because we standardize more, and now we are diverging. But it also means maybe that the industry is mature enough to actually having a branch of it, and I mean a branch, not the large majority, test something new, build a bone on something new. Again, it's not that we start with PERC immediately with 80%. We start, I won't say niche, but it starts small. So I think we need to pass through that. And yeah, it was mentioned before, how do you guarantee that companies provide this reliability, provide the guarantee, are able to back it up? This is probably a problem that maybe should not be necessarily discussed by the industry, but also by the regulator, that this became more clear, that the final user knows what you are getting, even when you get a new product. Just throwing this on the discussion.
Charlie, you've seen so much. So can we stem this? All these design changes, and I think you've shown many more actually that are possible.
And all of them have been used in the past, going back to the early 1980s. One comment, I'd like to sort of parse this discussion into two subtopics. So first, regarding the module and module quality, I find myself every so often going back to the basic module engineering design principles that Ron Ross and the JPL team published in 1984 as part of the Block 5 program at JPL, which morphed into our current IEC test protocol with some modest changes, but the design principles, including things like soiling, are detailed in those JPL reports that are still online, and thankfully now I can go online and find them. So I'm very confident about our ability to identify the design principles used to make long-lasting, high-quality modules. When it comes to the second topic here, wafer size. So the first time wafer size gambit was pursued was where I happened to work at Arco Solar in 1981. Everybody had standardized, quote unquote, on 100 by 100 millimeter wafers. Because we could grow our own crystal, we made 103 by 103 wafers. And we're able to make life difficult for copycats. If you look at where is roughly, I think it's probably 70 to 80% of ingot production for the solar industry today, mono production, is either Longji or Tianjin Zhonghuan semiconductor. So if I were one of those two ingot producers and had already engaged in cell, module, and power plant deployment, and wanted to, the risk is always, at what point do you alienate your customer? So I think, as a hypothesis here, it's possible that we're seeing a cycle towards a second level of shakeout. When I was working about 14 years ago at Applied Materials, I was living half my time in China, and I was working in serving 203 distinct solar manufacturing cell plants. Today, we look at the top 10 list, and I don't know, 9 out of 10, First Solar excluded, 9 out of 10 are mostly China. So if you are engaged in the competitive drive to lower cost and command the ability to control size, and I could obsolete equipment that somebody has already invested in downstream, because I've got the control upstream of the size of the wafer. It's a lever that's available to the manufacturer for competitive reasons. And we see sort of the same kind of gambit happening around, I've got a 600 watt, no, minus 650, no, minus 750 watts. That looks nice in a marketing press release, but what happens to the speed of deployment in the field? So there's aspects that are related to the physical dimensions that I think are addressable with a separate set of at least qualitative metrics that are disconnected from the quality metrics associated with module reliability and durability.
Okay, anyone else? Okay, then let's maybe just because this was a high efficiency, so I think that could have been the final statement. But since this was a high efficiency solar conference, let's maybe look at again back at the last 3 years that were pretty surprising. Of course, we saw that more or less a linear watt increase. Especially also if we look at tandem solar, which comes even beyond IBC or is the next step. I think the interesting thing is there was even an announcement from one company that they wanted to start production this year. I think it will be now next year. That's what they said for tandem solar cells in Europe. So what do we actually expect to see? When are we see next to Oxford PV actually others are coming up with some solution like this, and where do we see actually efficiency now going? I think so. Let's maybe, I don't know, everyone just 2 sentences. How do solar modules look like in 5 years? How you imagine them? Doug.
Yeah, I think that the majority will, vast majority will be single junction silicon. I hope that there's some, well, plus First Solar's CAD Telluride. I hope there's going to be some foothold tandem products that could then grow. But I wanted to point out something that Rado showed that I want to exhort everyone watching this. His chart with the LCOE of PV versus other technologies. I love that he just had the 2 points for each. So there's not all these curves that make it complex. There's the giant drop in LCOE from in PV. And even though we talk about going to 0 carbon, which we should for the modules, there's still the energy payback is less than a year. We shouldn't let new technologies feel they have to belittle what is going on now to justify the added value that they will create, because I think we're all making a positive impact.
Okay, great. I think if no one, Rado, okay.
Yes, so I'm the same opinion as Doug. Single junctions in 5 years, and depends on how China will also pick up on IBC technology. We saw that it took quite a long time to come to PERC, but then it went quite quickly. And of course, I believe that Oxford Power can bring this technology on the market, but then it's a huge bankability issue. I mean, I was organizing bifacial conferences since 10 years. And it was only a little change, and no bank was willing to give money for this technology. So I think this will be the same game as for bifaciality. I mean, then Oxford PV has to install with private money on or make small installations and prove it for many years that it's working in the field, and then maybe they can enter then the next level. And I mean, they are the first players in this field and will open hopefully this field for many other players, but this will take longer than we expect.
Yeah.
Yeah, well, I think the single junction is the backbone of the energy transition that is happening now and that will happen in the next 5 years and more. So that has to continue with that. It's not just a battle of one product on another. I like to see that there are early comers, like indeed we mentioned Oxford PV, that they will start to test the field, test how it's going on, start in a niche market. But we already see many industry, prominent industries that are present in this conference, big one, that are always looking at what's next. They need to keep on showing that there is possibility to increase the efficiency. So I expect indeed in the next 3 to 5 years, more than one, more than 2, 3 will start to pop up, starting to test, starting to put in the market some early product, and then the next will come in the next years. But by 2030, there will be very strong part on Tandem.
Okay, maybe Charlie, final words. I think we know what your personal choices you're betting on that, but what do you think in 5 years in terms of technology we will see mostly, and I think being the trend?
So I'm a chemist by background, and I think there's a great opportunity between single junction and tandem junction to apply the chemistry of photosynthesis, splitting high energy photons into 2 lower energy photons that are still in the collection spectrum for silicon. And there's a number of really cool materials that could do that and just serve that function as a coating on the front glass, so that the module efficiency will continue to climb and will make better use of high energy photons without needing the device physics of tandem junction. And I say that partly just to be different.
Okay, I think that's a nice final word, because in the end, as Doug said, everyone will contribute, and I think that's important because we have really a large task to stem if we really want to get to the terawatt production level, annual terawatt production level already in a decade, which is needed to really turn the path in terms of climate change. So I think
yes, and let's see if Charlie's down conversion will last for 50 years.
Touche.
We're upbeat. Okay, then.
There's some long-living trees in California.
Okay, wonderful. Then thanks so much. Just a few final words. Thanks to everyone, to my esteemed panel. Hopefully seeing you in person again as soon as we can all travel again, and there will be probably many others who are also yearning to do that with us. Thanks a lot to you. Thanks a lot to all the attendants who stayed with us on this first high efficiency solar technologies event that we organized at TaiyangNews. Thanks to our supporters, to our sponsors who all made that possible for us. Then I would say also take this opportunity, because we had so many great attendance, and since we want to do many more conferences and reports, we need to extend our TaiyangNews team. So if you're interested to work as a market technology analyst, doesn't matter wherever you are, we're a digital company, so you're invited to send us your CV. And finally, I would like to announce the next event. So on January 26, we will have our advanced module conference. We will launch our advanced module technology report. Radovan has shown one of the slides from one of the charts from the last one. We will do a new one. And here we will focus on where we address the needs of the different segments. So we look at different modules designed for different segments like utility scale, rooftops, commercial, and residential. That's the theme also of the next event. Again, thank you very much. And I wish everyone a very, very nice weekend.
Thank you, Misha.
Thank you, Michael.
Yes, thank you
very much.
Thank you.
Ciao, ciao.
Ciao.